Hello, my name is Akshay Kamath, and I'm going to be talking about a simple proof of a new disjointness problem with applications to data streams. This is joint work with Eric Price from UT Austin and David Woodruff from CMU. Let's start off with an introduction to the disjointness problem and communication complexity. Communication complexity is a common technique that's used to establish lower bounds on resources for different problems. Most commonly, it's used to prove lower bounds on the space complexity of streaming algorithms. We study the disjointness problem, which is a very commonly used problem to prove such lower bounds, and we study it in the number and the hand model. Informally, in this problem, there are t players, each of whom receives a subset of the indices 1 to n, and these players are promised that these subsets lie in one of these two cases. In the no case, the subsets are pairwise disjoint, and in the yes case, there exists a unique element from 1 to n that belongs to all of these subsets. The players are expected to communicate with each other in a communication protocol and distinguish between both of these subsets with some error probability. More formally, if we view the input to the communication problem as a matrix, which is a 0-1 matrix, each column of this matrix is input to a player. So player I receives column I as input. The players need to distinguish between the no case, where the sum of all of each of the rows is at most 1, and the yes case, where there exists a unique row whose sum is exactly t. There have been many papers that have studied this problem before. Alon, Matthias, and Jageri proved an n over t to the 4 lower bound in the blackboard model. Bar Yosef, Jairam Kumar, and Sivakumar proved an n over t squared communication lower bound in the blackboard model. Chakravarti, Court, and Son proved an n over t log t communication lower bound in the general communication model. And Gronomier and Jairam independently proved an n over t total communication lower bound in the general communication model. We will be looking at the blackboard model in this talk. And in this model, the messages of the player are visible to every other player in the protocol. So you can assume that each player writes his message on a blackboard. So how are these lower bounds for this communication problem applicable to data streams? In the streaming model of computation, elements arrive in a stream, and we wish to compute certain statistics of the frequency vector of the stream. So the frequency vector is a vector whose ith entry is the number of times that the ith element has been present in the stream. So each element arriving in a stream can be viewed as a linear update to the frequency vector. One very important problem in streaming algorithms is the problem of computing the pth frequency moment, which is the p norm of the frequency vector to the power of p. So we might wish to prove lower bounds for the problem of approximating the pth frequency moment with approximation factor p. We can prove this lower bound by showing a reduction from the disjointness problem. So in the disjointness problem, each player processes his input column as an input to the streaming algorithm and passes on the state of the streaming algorithm to the next player. And this is passed from player to player until every player in the protocol has processed their input in the streaming algorithm. The frequency vector of the stream that has been processed by the streaming algorithm is going to be a vector whose ith entry is just the sum of the ith row in this matrix. So in the no case, the frequency vector is a 0-1 vector. So the p norm of this vector is at most n. In the yes case, there exists one entry at which the frequency vector is t. So the p norm of the frequency vector is at least t to the p. So by setting t to be 2n to be 1 over p, we can use the n over t lower bound for disjointness to infer an n over t squared lower bound for FP estimation up to a factor of 2. So this gives us an omega of n to the 1 minus 2 over t lower bound for FP estimation up to a factor of 2. So why do we need to work with a new problem instead of disjointness? The reason is that the way disjointness is defined, it can be solved using n over t times log t many bits of communication. This is because using the pigeonhole principle, you can conclude that one player must have at most n over t many elements in his set. This player would just write out all of the elements present in his set on the blackboard, and every other player would just have to confirm that the set assigned to them intersects with this player's set. So given this limitation of the disjointness problem, we cannot hope to prove tight streaming lower bounds when the error parameter for the streaming algorithm is extremely small. In order to get around this, we introduce a new communication problem called mostly disjointness with t players. Informally, in this problem, there are t players, each of whom receives a subset of 1 to n, and the promise is that these subsets fall into either of these two cases. In the no case, the subsets are all pairwise disjoint, and in the yes case, there exists a unique element from 1 to n such that that element belongs to exactly half the subsets assigned to the players. So viewing this more formally, in the no case, the sum of each row is at most 1, and in the yes case, there exists a unique row such that the sum of the elements in that row is exactly t over 2. Phrasing the problem in this fashion doesn't change the reduction that we viewed for FP estimation much, and we can derive a similar lower bound in that case. However, observe that it's not as easy to come up with an upper bound for this new version of disjointness. So the theorem that we wish to prove is a lower bound on the randomized communication complexity of mostly disjointness with t players and n coordinates. The randomized communication complexity of a function is the cost of the cheapest randomized protocol that computes that function on every input with error at most delta. So the theorem that we prove is that for all error parameters delta, the randomized communication complexity of mostly disjointness in T is at least the minimum of n and n over t times log 1 over delta. In order to prove this, we prove a more restricted version of this theorem, where we show that for delta being very small, that is less than e to the negative 4t, the randomized communication complexity of mostly disjointness on n coordinates with t players is at least n. So in order to prove a lower bound for larger delta, assume you have an algorithm that solves mostly disjointness for a larger delta. You can use repetition to obtain an algorithm that solves mostly disjointness on delta less than e to the negative 4t, and uh, then infer a lower bound uh, on this algorithm. And that is how we go from the second theorem to the first theorem. So in order to prove the second theorem from the previous slide, we need to refresh certain definitions from the paper of Bar Yosef et al. Specifically, we need to look at the definition of conditional information complexity. So given a function f whose inputs belong to a set x, and another set D of auxiliary random variables. Suppose that the inputs X and the auxiliary random variable D are uh, picked from X cross D according to the distribution eta. And suppose that the error parameter that we desire for the communication uh, protocol is delta. The conditional information complexity of F with respect to eta and delta is the minimum mutual information between the input and the protocol on the input conditioned on the auxiliary random variable D, where the minimum is taken over all protocols that err with probability at most delta on every input to the protocol. Another theorem from the paper of Baryusov et al. Is uh, proven using an entropy argument, and this theorem states that the randomized communication complexity of any function f is at least um, the conditional information complexity of f with respect to any distribution eta. So in order to prove a good lower bound for the randomized communication complexity, we need to find a hard distribution for which the conditional information complexity of f is large. So the hard distribution eta that we pick for this problem is defined as follows. For every row of the input matrix, we pick a player, that is a column uniformly at random, and assign that player his input bit uniformly at random from 0 or 1. All other players in that row get the input 0. We repeat this process independently for each row of the input matrix. So here in this picture, we pick um, the red index in each row and we assign that index 0, 1 uniformly at random. This distribution is a product distribution over the rows and conditioned on the choice of the player within each row. The distribution is a product distribution within the row. So given that this hard distribution is a product distribution over the rows and within the rows conditioned on the choice of the auxiliary random variable, and also given the fact that mostly disjointness over n coordinates is just the OR of mostly disjointness applied row-wise, a direct sum theorem follows. And this direct sum theorem states that the conditional information complexity of mostly disjointness on n coordinates with respect to this distribution eta is at least n times the conditional information complexity of mostly disjointness on just one row with respect to the row-wise distribution zeta that we defined earlier. So it suffices to prove that the conditional information complexity for this one row is omega of 1 in order to prove an omega of n randomized communication complexity lower bound for mostly disjointness on n coordinates. So the lemma that we prove is that given delta less than or equal to e to the negative 4t, any delta error protocol for mostly disjointness with input drawn from the distribution zeta must have this conditional mutual information term being omega of 1. So let's dive into the proof of this theorem. In order to make this simpler for the talk, I will be restricting the proof to one-round protocols. The proof that we give in our paper is applicable to multi-round protocols. So we call a one-round protocol clean with respect to a player I if either the player doesn't observe his input message and his input and his message is independent of his input, or the player observes his input and the distribution of his messages on input 0 is disjoint from the distribution of his messages on input 1. So the claim that we have first is that in a one-round protocol, any player can be simulated cleanly, and if every other player in the protocol receives input 0, and we can simulate the protocol cleanly in a manner that player I um, observes his input with probability that's equal to the total variation distance between the protocol where he receives input 1 and the protocol where he receives input 0. So how do we prove this? Let us suppose that MI is the transcript of the messages sent before player I speaks in this one-round protocol. Further, suppose that D0 is the distribution of the messages of player I when his input is 0, and D1 is the distribution of his messages when his input is 1. We can simulate this player's turn as follows. Player I looks at his input with probability that's equal to the total variation distance between D0 and D1. And if he doesn't look, he picks from a distribution that is proportional to the intersections of the distributions D0 and D1, which in this diagram corresponds to the blue portion. And if he does look at his input, and without loss of generality, suppose that input is 0, he picks from the difference of uh, D0 minus D1. So he picks from the green portion of this distribution normalized to have probability mass term. So we showed in the previous slide that the probability with which he looks at his input is the total variation distance between D0 and D1. We show in our proof that in expectation over the transcript of the messages sent by the previous players, that is MI, this probability is the total variation distance between pi EI and the protocol on input 0. The second lemma that we prove is another lemma about clean protocols. So suppose pi is a protocol where every player is simulated cleanly. Further, suppose that player I uses bit with probability pi when every other player receives input 0. Further, suppose that the uh, sum of these pi's is at most t over 4. Then there exists um, a subset S of the players of size t over 2 such that with probability larger than e to the negative 3t, none of the players in S views their bit. This is a lemma that we can prove easily using the probabilistic method. So we use the claim and the lemma that we proved in the last few slides to prove the lower bound on the conditional mutual information. We start off by showing that the conditional mutual information term that we wish to lower bound is lower bounded by 1 over 4 times the expectation of the total variation distance between the protocol on the all zeros input and the protocol on uh, an input where only player I receives input 1 in expectation over all the players in 1 to t. A similar lower bound was shown in the paper of Bar-Yosef et al. In terms of Hellinger distances. So if the sum of the total variation distance terms here was t over 4, we would have proven the lower bound on the conditional mutual information term up there. So let's assume for the sake of contradiction that the sum of these terms is less than t over 4. When this is the case, using the lemma that we proved earlier, we know that there exists a set S such that none of the players in um, that set views their input with probability greater than or equal to e to the negative 3t. Let the uh, let e denote the event that none of the players view their input. Then let's consider this total variation distance term. So we wish to look at the total variation distance between the distribution of the protocol on input ES, that is every player in the set S receives a 1 and every player outside the set S receives 0, and the protocol on input on the all zeros input. So given the consequence of the lemma, we know that this total variation distance term is upper bounded by 1 minus e to the negative 3t. However, observe that this input ES falls into the yes case of the mostly disjointness problem on one coordinate. And the all zeros vector obviously falls into the no case of the mostly disjointness problem. So we cannot output the same uh, output correctly on both of these inputs. And since the protocol pi errs with probability at most e to the negative 4t, we also have that the total variation distance between the protocol on ES and the protocol on the all zeros input is at least 1 minus 2 times e to the negative 4t. So we've arrived at a contradiction, and it must be the case that the sum of the total variation distance terms that we spoke about on the last slide is at least t over 4. And consequently, the conditional mutual information term that we wish to bound is omega of 1. So let's wrap up the entire proof. So since the conditional mutual information term was omega of 1, when delta was less than e to the negative 4t, the conditional information complexity of mostly disjointness on one coordinate is omega of 1. Using the direct sum theorem, the conditional mutual information with respect to the hard distribution eta that we defined earlier of mostly disjointness on n coordinates is omega of n. And this implies a randomized communication complexity lower bound of n when delta is less than e to the negative 4t. Using the repetition method that we spoke about earlier, we can prove a randomized communication complexity lower bound for all delta greater than or equal to 0. So what are the consequences of proving this new lower bound for this new problem? The first consequence is in the area of LP heavy hitters. So in the LP heavy hitters problem, we once again want to find something about the frequency vector of a stream, and we are looking at this only in the insertion only model. The goal in the LP heavy hitters, in the epsilon LP heavy hitters problem, is to find a set S such that it contains all the elements that are whose frequency is epsilon times the p norm of the frequency vector, and no element whose frequency is much smaller than the p norm of the frequency vector times epsilon over 2 to the 1 over p. For the zero error epsilon L2 heavy hitters problem in the insertion only model, the best known algorithm that we knew earlier was the Misra-Gries algorithm, and this uses square root n over epsilon many words. The formal theorem that we managed to prove in our paper is this theorem, which most importantly implies that The lower bound for L2 heavy hitters, when the error parameter is 0, is square root n over epsilon. And this is tight up to a log n factor and improves the best known lower bound from omega of 1. In the frequency moments problem, we obtain a similarly tight lower bound. The previously best known lower bound was additive in terms of the lower bound in terms of n and the lower bound in terms of log 1 over delta, and was proven using a reduction from disjointness. And we prove a lower bound that is multiplicative in these terms. And our lower bound matches the upper bound of Braverman, Katzmann, Seidel, and Voranger. We also prove a lower bound on the low rank approximation of sparse matrices. In this problem, we see the rows of an n cross D matrix, one row at a time, and each row is of one sparse. And we wish to output a projection of rank k such that the error incurred in the Frobenius norm squared by projecting the matrix onto this projection P is at most 1 plus epsilon times the best k rank approximations error in the Frobenius norm squared. The best known deterministic algorithm for this problem was an algorithm by Gharshami, Liberty, Phillips, and Woodruff, and this achieved the guarantee using dk over epsilon many bits of space. And using a reduction from Moseley disjointness, we show an omega of square root d bit lower bound for the deterministic algorithm, and this shows that polynomially many bits are necessary in D. So let's just conclude with an overview of the results of our paper. In our paper, we define a new problem called Moseley disjointness to replace the disjointness problem. And we prove a communication lower bound for this Moseley disjointness problem that is simpler than the lower bound for disjointness and avoids using Hellinger distances. We also prove better lower bounds for many problems, like the LP heavy hitters problem and the FP estimation problem. We show an almost tight lower bound for deterministic or zero error L2 heavy hitters. And we show a first polynomial lower bound in D for the low rank approximation streaming problem. Thank you.